Okay, as you'll remember, we were talking about the very introductory properties of what kinds of physics quantities we describe with scalars and vectors. And just to review a little bit, we said a scalar is another name for a real number, whereas a vector is something that specifies both how much, how big the strength is, or the quantity, like how fast something is going, and the direction in which it's directed. Okay, so examples of vectors in physics were forces, velocities, accelerations. Scalars were like temperature, volume, that kind of stuff. Now, let's get into a little bit of the notation. You know, we're used to thinking of x as standing for a particular x coordinate. You know, we want to use these variables to stand for things, and we want to be able to look at a variable and know whether it stands for a vector or a scalar. So when we use a letter to describe a vector, we're always going to, in order to tell us that it is a vector, that it has a certain direction, we're going to put a little arrow over the top of the symbol. So when I say I'm going to represent a displacement, say in 3 dimensions, by a vector, you know, something started here and ended up over there, it has a certain direction in which it moved, I would use a symbol that describes the fact that it's a vector. I'm going to put a little arrow over the top of it. And because we're lazy, it's easier to write it if we just draw an arrow with only half an arrowhead on it. You know, you could put the other half of the arrowhead on it, but it's just easier with one, you know, swipe of the pencil to go up like that. F is a force, so force is a vector, so we will give variables that look like that. In contrast to that, we're going to use plain letters to describe or denote a scalar quantity. So we'll say things like V is a variable that represents a volume. T is a variable that represents a temperature. There's no direction, so we don't put an arrow over it. All right, so let's get into how exactly we're going to specify vectors, and we'll start out with the idea of visualizing them. So in this particular example, I'm going to imagine an ant has a certain displacement between times t1 and t2. And if we're thinking of this as an example of one-dimensional motion, you know, in other words, the ant is walking on the x-axis, and I mark t1 position and the t2 position on the x-axis, then a reasonable way to visualize what the displacement is to draw a vector that draw an arrow that starts at t1 and ends on t2. In other words, we're representing this displacement vector by saying the ant went from there over to there, right? From t1 over to t2, those positions on the x-axis, okay? Similarly, now that we're talking about 2D and 3D motion, so in 2D motion, maybe the ant is walking around in the xy plane, and at time t1 it was here, and it walked on some weird path, and at time t2 it passed this point over there. What is its displacement between time t1 and t2? We want to do the same kind of thing. Draw an arrow that goes from its starting point to its ending point. And so this would be an arrow that represents the vector d, which is the displacement from t1 to t2. Okay, so that's one way to specify a vector. We could say, draw an arrow. The length of the arrow represents the magnitude of the vector, and the direction that the arrow is moving in, going from tail to tip, tells us the direction of the vector, right? If I wanted a bigger displacement, it would go further on along that direction. So we can see both the magnitude of the displacement and the direction by drawing an arrow. Now, arrows are good for developing our intuition. They're not so good to calculate with, so it might be better if we could more precisely specify what this vector is in a way that we can calculate with numbers. So an alternative way to specify what this vector d is if I turn this vector into a right triangle by starting at the tail, first moving only along the x direction, and then moving only along the y direction to get to the tip. The size of those two sides, the non-hypotenuse sides of the right triangle that I have created, are what we call the components, the xy components of the vector d. So a second way to specify a vector is to give the x and y components of the vector. You'll notice that if somebody says, hey, the displacement is so long and going in that direction, I'm going to tell you that to get from the tail to the tip, you move 3 units along the x direction and then 1 unit along the y direction. That's as good as knowing what the arrow is. So if I give the dx and dy, I know enough to reconstruct the arrow. So it's an equivalent piece of information. And if somebody draws the arrow for me, I could extract what dx and dy were as long as I knew the direction of the xy axes. Excuse me. So in this example, dx is 3 meters and dy is 1 meter. A third possibility is given by, that sort of r theta representation for a vector. So if I wanted to specify how big and in which direction this vector is pointing, I could give the length of the vector. In this case, I would have to use the Pythagorean theorem. The length of the vector would be the square root of 3 squared plus 1 squared, the square root of that number, and its units would be meters when I calculate it. So when I calculate the square root of 3 squared plus 1 squared, that's 3.16 meters in this case, because the 3 and the 1 have units with them. And how do I calculate this angle theta? Well, I could use some of our right triangle facts, like the fact that tangent of theta is opposite over adjacent here. So tangent of theta is 1 over 3, and therefore theta is the inverse tangent of 1 over 3. So I go into my calculator. You do have to be careful when you're taking cosines, sines, and tangents, or inverse cosines, inverse sines, inverse tangents, that if you want your answer to come out in degrees, you need to make sure your calculator is in degree mode. And that's, at least on your typical TI calculators, there's a mode button and then you select degrees as opposed to radians. And when you're taking the cosine of an angle, if you want the angle to be interpreted in degrees, you want to be in degree mode. So I could calculate what that angle is. And notice that if somebody tells me relative to the x-axis direction, which is along this direction, if you tilt up by an angle theta, and I tell you what theta is, maybe it's 30 degrees, and then you go so far out along there, starting from the tail, that would tell you exactly what the tip was. So that would be an equivalent thing that could get you back to a picture of what the arrow is. So all three of these specify the same information, but some of them may be more suited towards certain kinds of problems or describing what information we know in a problem or giving a solution to a problem. We'll see examples of all those later on. Now, just a couple of facts about these. First of all, in this particular case, dx and dy are both positive. They were positive 3 and positive 1 because what defines the sign of them is you always say, in starting at the tail of the vector and going from the tip, first along x and then along only y, how far do I go along x? And in this case, x increased by 3, and that's why dx was 3. And y increased by 1, and that's why dy was plus 1. If, for example, in going from tail to tip, x decreased, then you would put a minus sign in front of that. So if in moving from tail to tip, if the x-coordinate decreases, then dx would be less than 0, and so on. So always go from tail to tip and first figure out the signs of your components, the x and y components. Second note is that sometimes we'll specify negative angles. We could, if I said the angle is 180 degrees, that would mean my vector is pointing over to the left, right? Because I would start over here and go all the way around to 180 degrees. Now, if I wanted my vector to go down here, maybe I might say 360 degrees would be all the way back to 0. 350 degrees would get me just 10 degrees below there. So I could use 350 degrees, but a lot of times people like to say minus 10 degrees. So if someone gives a negative angle, what you do is draw the direction from the tail that goes parallel to plus x, and if you have a negative angle, it opens downward from there. If you have a positive angle, it opens upward from there. So you got to be aware of what those angles mean. All right, here's a voting question just to check your understanding of the definition of components. You don't need a calculator to answer this. you should be able to pick out the best answer just because the other ones, if you understand what to think about, don't make any sense. Here's a vector that has a certain length. What are the x and y components of the vector? And you should choose the best answer without going to your calculator, which is the only possible one of these that could possibly make sense. Okay, in order not to wait too long, I'll say again, pause the video if you want to think about it, and you really should come up with your own answer before you listen to the solution. The solution is, well, the way to think about it is, to find the components, what I do is go from start from the tail, first go only along x, and then go only along y. And I have to look at the sign of the change in x. So look, x decreases, y increases. So that means the x component should be negative and the y component should be positive. That narrows it down to B and C. They're the only ones with negative x components and positive y components. And furthermore, I can see that from the angle of this, I have to go a shorter distance along x and a longer distance along y. So I want the one of these two where the y component is bigger in magnitude, and that singles out selection B right there. So that's just testing whether you have some intuition about components. And you know, a lot of times the first time people see that, that's kind of confusing, but that's why we're introducing it here. All right, let's start off with the worksheet that should be in the middle, posted in the middle of these videos on the course website. So we're going to answer both parts. That's a little bit confusing labeling here, but there's a part capital A, which is above here, and part capital B. I want you to do both of them. And the idea is we're given some x and y components, -4 and +1, and we want to draw a vector that has those components where the tail is attached to the point 1, 3. Okay, so x equals 1, y equals 3. That's this point right here. And we're also going to do the same thing for a vector that has an x component of 4 and the y component of -1 with the tail attached at the same point. Then down in B, we are going to convert to the length and angle of those vectors. In other words, what is the length of that vector, and relative to the plus x direction, what is the angle at which we have to draw that vector? So see if you can figure those out, both for A, which refers to the one directly above, and B, which refers to the one above here. And when we come back, we'll discuss the solution, which is going to lead us into a little bit of a warning for calculating angles. All right, that's the end.